Okay, 2 o'clock, everybody. Welcome in. ME2001, week 6, pressing on. All right. Announcements. You got a homework due tomorrow, which is Wednesday. It's on couples and couple moments. So a little bit more complicated of a homework, really diving in on some deep topics with moments and couples. So really give it a go. Really make sure you understand everything that's happening in that homework. If not, come see me in office hours tomorrow morning, 8 a.m., 9:30 a.m. All right. How do we like to joke today? I wanted to post a joke about sodium, but was like, nah, people won't understand. This person's comment is also hilarious. Post it anyways. Most people are smarter than you are think and will probably understand it. Oh man, I don't know about you, but that English ain't so great. Yeah. Right. So that's kind of funny. All right, so let's get on with it. New topic today. I posted a new set of lecture notes. Most people are smarter than you are think. Oh, my hair. I got a comment about my hair. Yeah, I was grading all the exams for my other class last week, and all my hair fell out. What the heck? I was just doing it, and then all of a sudden I looked in the mirror, and it was all gone. I'm not bald. I'm balding. Okay. All right, new topic today. So new note's been posted, and the new topic today is getting away from the in-depth conversation about moments, and now we're going to apply some of the things we learned about moments, and we're going to apply it to 2D rigid body equilibrium. Okay. I've kind of emphasized this in the past, but getting comfortable with vocabulary as an engineer and just generally as a scientist or whatever you're going to do in your career is going to be important. And so when you think about the words that are sort of in conjunction here, 2D rigid body equilibrium, those should spark some ideas or some thoughts about equations or what's happening physically with what we're going to talk about. So, 2D, that's pretty straightforward. Usually things contained in like an XY plane. So we've sort of done a lot of that sort of stuff. Rigid body, we've talked about what a rigid body is. It's a object that has volume and mass. And then equilibrium. We've talked about equilibrium previously in this class, where we talked about particle equilibrium. That had a very specific definition in terms of our statics class. That was the sum of the forces on a particle have to be equal to 0 if it's going to be in equilibrium. And we're going to enact something like that now, but not this case for particles, but for rigid bodies. So let's dive in on this topic, all right? And let's sort of refresh ourselves what particle equilibrium was. Well, first, let's review particle equilibrium. Okay, this is very simple. If in equilibrium, this is specifically for a particle, we require that the sum of the forces on that particle equal to 0. We did this for the first, 3 or so weeks of the class after we introduced what a vector was, what a force was, all that stuff. Then we did 2D and 3D particle equilibrium. And the sum of the forces equal to 0 was like the basis of all of that work. And so in 2D, that was sum of the forces, which we generally said was sum of the forces in x, I hat, plus sum of the forces y in j hat had to be 0. And since, the I and the j directions are kind of independent of each other, we deduced in that general sense that the sum of the forces in the x have to be 0, and the sum of the forces in the y have to be 0 independently for this equation or the state of equilibrium generally to hold. Both of these things must be true. The sum of the forces in the x equals 0, and the sum of the forces in y equals 0. So that's where we started with 2D particle equilibrium, and then we moved on. And in 3D, very similar idea. in that for a particle, for equilibrium to hold, some of the forces in x equals 0, some of the forces in y equals 0, and some of the forces now in z equal to 0 if we're talking about 3 dimensions. This is particularly in rectangular coordinates. All right, so that's for a particle. So we got like these, in 3D, we've got like these 3 equations. So for a particle, you end up with these 3 equations. And we saw all sorts of examples of how we might apply this. I could think of a bunch of homework problems that looked like you had a particle that was here and it was being held by 3 ropes. It looked like that, and then there was some weight on it. And you were told some tensions here. Here's like F1, F2, F3. And then you had homework problems that were like, what are the tensions in the ropes to keep this particular system in equilibrium if the weight of the object is X? Okay, had a bunch of homework problems like that. You had one question on exam number 1 that looked a lot like that. So you had a lot of practice doing things like that. Now, what's different about rigid bodies that is not the same with particles as we move this idea of equilibrium from particles to rigid bodies? Now we're going to have full bodies that are not just this one little point in space. So the difference between particles and rigid bodies is that rigid bodies have volume. Okay, so let's be very clear here. So now move to rigid bodies. And what's the difference between a particle and a rigid body? Well, particles and rigid bodies both have mass. But only rigid bodies have volume. Okay, now why is this important? Well, when we had a particle in space, there was only really one location on that particle that forces could act. It only has one point in space that it occupies. But when we're talking about rigid bodies now, we have these objects that have volume. And if you have a volume, there are many points on that volume where your forces can act. And because there are many points on your body where the forces can act, we can now have moments that are generated on your object. And so you're talking about distances between various particles on the object and forces acting on those various pieces. You can generate moments on your object, which we now have to consider that we didn't have to consider with particles. So what do I mean by that? So because of this, we must now consider moments. Okay, so this is an important addition when we're talking about moving from particles to rigid bodies. Rigid bodies have volume, so forces can act at many locations on that rigid body and generate moments. All right, so that leads to kind of the general idea for equilibrium of a rigid body. Okay, so for a rigid body to be in equilibrium, we're still going to have the same general idea that the sum of the forces on that rigid body is still going to have to be 0. But now we have an addition that the sum of the moments will also have to be 0. If this thing is not translating or rotating, it's fully static, and everything is going to have to balance out. So to enforce equilibrium of a rigid body, both the sum of the forces and the sum of the moments must be 0. Acting on that body must be 0. Okay. I'll give you the kind of the wording definition here. This is sort of like the English written definition. And we're engineers, so we like to speak in math language. And so this is it written in English speak, but in math language. That is the following. The sum of the forces that act on the object equals 0, and the sum of the moments that act on the object must be 0. I personally like that math language because it's a lot less writing. Okay, so in 2D, this is, let's start with 3D. I think that's pretty obvious. In 3D, you're going to have like the sum of the forces equal to 0 leads to sum of the forces x equals 0, sum of the forces y equals 0, sum of the forces z equals 0. And now we're also going to have our moment contributions. Leads to sum of the moments in the x direction acting on the object are 0. That is the tendency for all the forces to create rotation about the x-axis. That's the sum of the moment in the x. Sum of the moments y equals 0, and sum of the moments z equals 0. Okay? So in 3D, this is actually 6 equations. Okay. Getting complicated, I know. So this is sort of the most general case, but we're going to start with, at least for now, 2D equilibrium. For now, we start with 2D equilibrium. Okay. And the most general case, which you'll probably see most often in this class, but you know, not always. Most generally this is the sum of your forces in x equals 0, the sum of your forces in y equals 0. So those are sort of your force equilibrium equations. And you know, we saw a lot of this with our 2D particle equilibrium. And then surprisingly, we only have one more addition here, and that is that the summation of the moments in z must be 0. Okay, now why is that? Well, remember that the moments we generate is something like r cross f. If these guys are only contained in I and j, then the only possible moment that you can generate, if you're only considering forces in, you know, the I and the j direction, you can only generate moments in plus or minus k hat. If you're thinking about a two-dimensional problem where all your forces are in that sort of xy plane, and you only have forces that act in that xy plane, and your position vectors are only located in that xy plane, then the only moments that you can generate will be in this plus or minus k hat direction. And so because of that, the only real addition when we're thinking about rigid bodies to 2D equilibrium comes in this form of the summation of moments in z being equal to 0. Okay. So that's the basis for equilibrium. You've already done a lot of this with particles, so I'm not going to really dive in on this too much right now. The math I think you get, the math you understand, you know what vectors are, you know what unit vectors are. You can understand that the I, the j, and the k directions are all independent of each other. That's how we get all these individual equations. That stuff you all get, or you should get at this point. But one last thing that we sort of have to hammer out and work through is new free body diagrams that are going to be a little bit more complicated, because now we're not talking about just single particles, but we're talking about bodies. And I've talked about this a little bit in the past. We've talked a little bit about free body diagrams of rigid bodies, but I really now want to hammer this home and make sure that we're fully aware of all the ins and outs that go along with creating free body diagrams of rigid bodies. So let's do that and have an aside really quick on free body diagrams for rigid bodies. Okay. And I've talked about this before, but when you have a space diagram that you want to make into a free body diagram, you have to isolate that object. Okay? So generally, we go from space diagram to free body diagram. Okay? And the way that we do this is we pick the body or the particle of interest and we isolate it from its surroundings. Okay? So we select particle or body of interest. Then we isolate that body from its surroundings. Okay, so you basically like draw a contour around that particular object, and wherever you are isolating that body that might be in contact with another body, you have to account for the force that could be transferred between the two. Okay? So we isolate body from surroundings, and we account for forces and moments generated by isolating. Okay? And generally, we call these reaction forces. And also reaction moments. Okay. Let's look at an example, and this is an example from the slides. I'm not going to try to draw this because this is not my specialty. Let's say you have sort of a skid loader that's got some load in it. Looks like this. Okay. So here's this truck. We sort of like looked at things that have, you know, we've sort of talked about going from a space diagram to a free body diagram. Okay, so if this is your space body diagram, or your space diagram, a free body diagram, we're talking about isolating this particular guy from its surroundings. All right, and so you would say, all right, I want to draw a free body diagram of the tractor. It's a skid loader, but okay, let's call it a tractor. Okay, so we create a contour around this particular guy. I've sort of done this before. And anytime we have to cut through something else where the body is in contact with that piece, we have to account for the forces that are sort of resisting that motion. Okay, so I'll come back to that in a second. We're creating this outline, tracing this outline around this particular guy. And here I'm going to do something a little bit unusual, but okay. That's basically the outline of this particular guy. All right. Now I think about, and I've talked about this before, I had to like cut through the ground at the wheel here, and I had to cut through the ground at the wheel here to isolate this tractor. And so I'm going to have to account for the forces that are generated when I remove that tractor from it touching the ground. These are these reaction forces that I'm talking about, okay? I also have to account for the internal weight, which for this guy is just going to be the weight of the tractor, and also if I'm considering whatever loads inside here, the weight of the load. So if I were considering all the things that I had to account for when making the free body diagram of this particular rigid body, it would be the weight of the load, the weight of the tractor, and whatever forces are happening at the wheels when they're touching the ground. All right. So my free body diagram in the end, and again, this is in your book or in the notes, looks something like this. All right. So you've got some of those critical pieces of information in this particular figure that you can see. Again, the weight that I talked about. You've got, the bucket load, which is kind of inside of the load here. They've included the weight of the arm, which I guess they're considering separate from the weight of the whole tractor itself, which is fine if that's the way that you want to do it. So the boom weight is something they're considering separate. And then your reactions here. Okay, so you see this term reactions. That's referring to the reaction forces that are occurring at the wheels when you cut away the ground. What you'll notice here is that on the front wheel, they have sort of this like front wheel reaction, which is this force that's stopping the truck from moving through the ground. That sort of makes sense. If you thought about if the ground wasn't there, the truck would fall. And so to prevent the truck from falling, the ground has to provide some vertical force to stop that tractor from falling. Okay. You've got a similar looking force at the back wheel here, which is, again, stopping this guy from moving downwards. And then you have sort of this surprising one here, which you may not have thought about, is this horizontal reaction. And this just comes from the friction of the tires on the ground. Okay, there's some frictional force that's holding this particular tractor in place. We're going to talk about that in just a second. But the idea here, and what I want you to get away from this particular lesson, is that we started with some object that we wanted to isolate, which is here. And we drew lines around that object, isolating it. And every single location that we drew a line that went through something where our body was in contact with something else, here the ground, over here the load and the tractor, we had to account for those forces that were there, okay? And so we're going to do a little bit of example, and we've seen some examples of this in the past, but I just want to hammer these guys home, okay? So let's now consider one more example with a common object, and we'll actually draw this one instead of bringing in the picture from the slides. Let's do an example with a truss. And trusses are very common in engineering. If you've ever driven over a bridge ever in your life, you've probably seen some sort of truss structure. And trusses are powerful because of their load carrying capability and their ability to share load over multiple members. And we're actually going to have about a week or so of just looking at trusses generally later in this class after your second exam. But for now, let's look at them with a broad stroke of kind of considering a free body diagram of a truss and how we might break it down. All right, so let's consider a truss. With 3 external loads. And we'll call them P, Q, and S. Okay, so let's draw, oh boy, let's draw what that might look like. Okay, and so I'm just gonna create sort of a very basic looking truss structure here. Think of each of these lines as a beam inside the truss, okay? And this is the same picture that's actually in your notes, okay? Down here, I'm gonna make something that looks like this. I'll talk about what that is in just a second. And over here, I'll make another item. I will talk about this in just a second. And we're gonna draw our forces that are acting on this truss. Okay. So maybe that's your P, here's Q, and here's S. All right. Now, this would be considered a space diagram, right? It's a diagram of an object that we're interested in analyzing, okay? And here's a truss, and I have many ways to sort of isolate this truss. And I think the easiest way that you might consider analyzing the truss is to isolate it by sort of just drawing this circle around it, right? So, here we are sort of isolating this guy. And what I have to do is I have to isolate by sort of removing what's happening with this guy down there, which I'll talk about in just a second. And I also have to sort of think about removing or adding reaction forces for whatever's happening down in that lower right corner. So here's like my isolation box. All right. I'm so lonely in my isolation box. This is how I feel when I'm at home these days. All right. You're isolating this. And so now if we consider the free body diagram, again, you're going to be left with your truss. So basically the same shape that you started with. Okay. And those same forces. The external forces are still there. They did not go away. All right. I've now got to consider what's happening at these guys down here. All right. And when you're looking at engineering problems and thinking about how you want to represent with a drawing things that are actually happening, you need to sort of use some shorthand symbols that represent the actual world. Now, let me explain what I mean. So these symbols here are very specific. The triangle and the circle in 2D, they stand for a very specific set of reaction forces that I'm hoping to represent with this particular picture. And in this particular situation, this down here is a pin, okay? And it has 2 reaction forces associated. Okay? That's that triangle with the sort of dash there. So if I wanted to represent the reaction forces associated with a pin, I can do that with 2 forces that are orthogonal. And let's say that this is point A. I'll just make up some variable here. This is point A. So I'll say here that this is the force at A in the y direction. This here is the force at A in the x direction. Get your facts straight, okay? That differs from this reaction force over here. And this symbol has a very specific meaning in engineering as well. And this here is called a roller. Okay? And this is one reaction force. And so in this particular situation, let's call this point B. You would represent what's happening at that location with something like force at B and Y. Notice here I haven't added the X force, and that's because this particular type of reaction would not call for that resistance in that direction. Now, it sort of makes sense when you think about the names of these particular reaction forces. Okay, if I thought about what is a pin, okay, if I thought about this particular structure having a pin passing through point A, well, if I was pinned at point A, I wouldn't be able to move that structure left or right or up or down, okay? So that reaction force, this particular pin, would stop the motion of the truss in both the left and the right and the up and the down directions. And so to account for that, I'm drawing the resistance to that motion, which would be this force in the X and the force in the Y, okay? Pretty straightforward, easy to understand. That's different from this roller reaction, which you see over here, and named as such in an appropriate way. If you thought about the truss just resting on like a cylindrical object or like a set of bearings, for instance, yes, you would stop that truss from moving down into the ground, but you would not be able to stop that truss from moving left and right at that location. So you wouldn't have any force resisting your motion of that truss left and right. And so because of that, the roller only resists the sort of motion of the truss downwards, and thus it can only really apply force upwards at point B. And so when we break through or sort of break away a roller from our original space diagram, we're only including one particular force. Okay, so we've got our forces now that are accounted from our reactions. We also might want to include the weight of our object. The center here, let's just call this the weight. You know, that's the internal force that we need to account for. If I was considering trying to solve this particular problem, if I knew P, Q, and S, I could solve for FAX, FAY, and FBY with some of the forces X equals 0, some of the forces Y equals 0, and some of the moments Z equals 0, right? I have 3 equations and 3 unknowns. Some of the forces in X, some of the forces in the Y, and some of the moments in Z would give me 3 equations. And then in this situation, I could solve for my 3 unknowns, FAX, FAY, and FBY. I guess we would have to assume that we knew what the weight was also. So I guess we'll throw that guy in there. All right. So we're building on these ideas and building these concepts of how do we create free body diagrams appropriately, and how do we model real connections using appropriate reaction forces, all right? This was just one simple example using probably the most common reaction forces. That's this pin and the roller setup. But there are many, many sort of reaction forces that you could imagine. We've seen another type of reaction earlier in the class, which was just your basic single cable. So we talked about a single cable that connected to like a pot or it connected to your lamppost. When we isolated the particles previously and we cut through a cable, we're actually drawing a tensile reaction force in place of that cut cable that we originally used. So that's one specific example. There are many reaction forces that you might see and many types of boundary conditions that would be associated with various types of reaction forces. Inside your notes, I've provided you with a chart that has the most common 2D reaction forces. And this is in your notes. You're probably not going to have time to sort of copy this down, but I just want to bring it to your attention, okay? So we've talked about rollers. I just sort of explained what those are. They're typically represented in, pictorial form with something that looks like this. We just saw this in our truss example. You could have a rocker, which is a very similar idea in that it, has the ability at that location to move left and right, but doesn't have the ability to move through the ground. And you could also have some beam that's resting on a frictionless surface. You are not able to move through the ground, but you can slide freely on that frictional surface. All of those would lead to a single reaction force at that location that if you wanted to isolate, let's say the ground, the rocker, the rollers, you wanted to isolate those from the body of interest, you would replace those individual boundary conditions with that one single force. Same idea with like a short cable or sort of this short link. We saw a lot of cables in the beginning of this class, and I didn't really talk in great detail about how we're appropriately replacing them, but now you know that if you have a cable in a certain direction and you want to isolate that object, let's say this is our isolation box, well, we would replace what's ever happening in that cable with a single force in the direction of that cable. Right? Same thing with a single link. Right? The difference between these two situations, if you want to get really technical about it, is that the link could provide compression where the cable could not. Right? It's going to be important in our truss conversations later. All right, let's continue. This one occurs a lot, this kind of like collar on a frictionless rod or a pin inside of a frictionless slot. This is another one that's common occurrence. And in this situation, you would be free to sort of move along the rod. And in this situation, you're sort of free to move up and down the slot, but you are not free to move in this general direction. You're restricted by the rod or restricted by the slot from moving sort of in the direction perpendicular to the slot. So you have one force here that you would represent as sort of the force that's resisting your motion, and that force would be acting perpendicular to the channel or perpendicular to the rod, stopping your motion there. Okay, so those are all sort of like single reaction forces. Now, we also have to consider those, double reaction forces. And I showed the pinned ideas before. And so this here would be like a pin from your previous example. You can sort of rotate freely at this pin, but you cannot move your object left and right. And so you would represent removing that pin with two reaction forces, one left, one right. Same idea with this rough surface. Okay, you're not able to pass through the ground, so you need this force that stops you from passing through the ground. But also because this surface is rough, you're not able to move left and right with this particular object. So you have to account for the fact that when you break away that rough ground, it's providing you some resistance left and right. Lastly, and this one is one we haven't quite talked about or seen yet because we have to include moments in the discussion now, is a fixed support. And this one is very common when you think about like, think about a stoplight that's extended off of a beam that's out of the ground. Okay, it's a cantilevered end. Many examples that exist in real life. Here, the idea is this particular object, if I'm going to break it away, yes, it's true that it's not going to be able to move left and right. It's not going to be able to move up and down. So I have to account for the forces there, preventing it from moving left and right and up and down. But also, unlike all the other ones here, this is not free to rotate. Okay? So I have to account for the fact that this particular support does not allow me rotation. And the way I do that is by accounting for or putting a moment at that particular location, which is resisting any sort of rotational motion at that particular location. All right, so those are probably the basics for two-dimensional reaction forces. All right, now let's finally go through an example using some of these ideas. Okay, I'll just see if I can bring all this in here at once. So we've got this crane here, mass of 1,000 kilograms, used to lift a 2,400 kilogram crate. Held in place by a pin at A, okay, important, and a rocker at B. Center of gravity at the crane is at G. Determine the components of the reaction at A and B. Okay. Give you maybe another 30 seconds, and then we'll get to this. If you're kind of finished drawing this object, maybe you want to think about making a free body diagram. Okay, so the idea here is that we've got this crane. It's lifting up some load. It's got some weight itself. And we're interested in determining what's going on at point A and what's going on at point B. It's specifically asking me the components of the reactions at A and B. So what are the reaction forces at A and B is what it's sort of asking me. Okay, now to execute this problem, I need to isolate this crane. And so obviously to do that, I'm going to sort of isolate this guy by sort of drawing this sort of isolation box around it, right? And I notice when I do that, that I'm cutting off a pin here at A. Remember, our pin is 2 reaction forces, and I have a rocker here at B. And the rocker is only 1 reaction force, and the reaction here is going to stop sort of the point B from moving left and right at this location. I'm also cutting through the rope here that's holding up my 2,400 kilogram mass. So let's go ahead and make the free body diagram with that idea in mind. I'm going to make a very crude free body diagram here. So here's my crane. I'm not going to draw in all the truss structure. It's really not that important. Here I've got a pin at A. So I've got a force at A in the X direction. And here I have a force at A in the Y direction. That's from that pin. These are 2 forces I need to account for. At B, I have a rocker that's stopping my motion left and right. So my force will also need to be in this horizontal direction. Force at B in the X. I'm told that this crane has some weight. I'm told it acts at point G, it's 1,000 kilograms. So doing some math here, this is 1,000 kilograms times 9.81. This will get me 9.81 kilonewtons. All right, just quickly there, we want to write forces here. 1,000 kilograms is a mass, not a force. So we want 9.81 kilonewtons there as my sort of weight of the crane itself. And then we also cut through this rope. Remember, I've got to include that. Here, the sort of the weight of this particular object. This is 2,400 kilograms. Times 9.81 meters per second squared. It's going to get me 23.5 kilonewtons. Okay, and those are all important pieces of information. So with my free body diagram here, I've got basically everything accounted for. I've got the weight of this piece. I've got the weight of the load that it's lifting. And I've got these sort of 3 reaction forces that are occurring that I want to solve for. So these are the unknowns that I want. We're told that it's not moving, so we have equilibrium. So I'm going to do something like sum of the forces x equals 0, sum of the forces y equals 0, and sum of the moments in z equals 0. And here I have my three equations, 1, 2, 3, and I'm going to have three unknowns in this situation. 1, 2, 3. And so I'm ready to go. All right. So we could start with any of these equations, but let's start with the moments. And you can pick any point on the structure to sum your moments equal to 0. Doesn't really matter where you select to do this. So let's go with point A. It's going to make our lives easiest to select point A because we have two forces that are acting through A. And if we select to sum our moments there, we don't have to worry about the contributions of those forces. So let's roll with that idea. Sum of the moments in the z direction at point A equals 0. All right, so I'm standing at point A, and I need to know the contribution to the moment from this 9.81 kilonewtons, this 23.5 kilonewtons, and this force Bx. Right. I'm going to cruise relatively quickly through this. We should all sort of be comfortable with these moment calculations quickly, or at least getting there relatively quickly. Here I see the distance from A to B is 1.5 meters. This is a perpendicular distance from the line of action of that force and where it's acting. So I can just straight away here understand that if I'm standing at A, here I am, standing at A, I stick my arm in the direction of that force, I curl my fingers in the direction of that force, my thumb is going to be pointed towards me with a positive K hat. So the contribution from that particular force is going to be something like 1.5 meters times force Bx, and this is going to be in the positive z. So since I'm doing this in z, I'm just going to keep it as a positive value. I have to contrast that with what's happening with these weights. Okay. Now if I'm here standing at A, and I stick my arm in the direction of that force, and I curl my fingers downwards, my thumb is going to be into the page. So this 9.8 kilonewtons is going to contribute a negative moment for me through this moment arm of 2 meters here. So here then I'll have a minus 2 meters times 9.81 kilonewtons. All right. Similar idea for this 23.5 kilonewtons, same directionality, but now a longer moment arm, which is 6 meters total. And in this situation, the only unknown is this force at B and X. And so this is just algebra here. And this will leave us with the force B in the X direction is going to be 107.1 kilonewtons. Okay, so that's what we find with our magnitude. And this will be, if we want to be very specific, this is acting to the right, so it's an I hat. I haven't written it as a vector, but my force at B in the X, I've drawn it in my free body diagram to the right. So this is 107.1 kilonewtons to the right, or in I hat. I can sort of enforce my other equilibrium equations now. Sum of the force in X equal to 0. I go up to my figure here. The only forces that are acting in X are this FBX and this FAX. Based on how I've drawn them, they're both acting to the right. So we have force at A in the X plus force B in the X equal to 0. So what you'll see here is that the force at A in the x direction is the negative of the force B in the x direction. Or that the force at A in the x is negative 107.1 kilonewtons. All right. So that negative sign would indicate that, it's acting to the left. We've generally drawn the free body diagram to have this force acting to the right. And the negative sign indicates that, the way that we drew it initially in this picture was not accurate. We should have drawn it to the left, but we didn't know that beforehand. So we just let the math take us there, and the math will tell us that it's the other direction. All right. I realize we're 1 minute late. Apologies. Let's just run through the force in the y direction quickly. This is pretty easy. You have that the force acting at A in the y direction, your last unknown, minus the weight of the object, 9.81 kilonewtons, minus the load, 23.5 kilonewtons, equal to 0. You work through this. The reaction force at A in the y direction, 33.3 kilonewtons. Okay, so that is our very first step into 2D rigid body equilibrium. That's it for today. Kept you 1 minute late. Sorry about that. We'll do a couple more examples tomorrow. See you then.